All right, we're going to wrap up this chapter on functions of two variables. Well, derivatives of functions of two variables. We'll be looking into integrals later on, but we're going to look at a special kind of method that works for finding maximums and minimums when you have a constraint on a function. And so to try to kind of motivate this, I want you to think about the level curves of a function. Okay, something like this. And then let's say we have some sort of region, and we're interested in finding the maximum minimum values of the function on that region. So I'm going to just like draw a region like this. Okay. So now here's the thing that you want to kind of realize. Maximum and minimum values are going to occur when you have, so if you look at the level curves, right? So here I'm going to extend this level curve out. Like imagine this would be a level curve that would be tangent to this boundary. Over here you would have another level curve that might be around here or something like that. I'm going to see what are the level curves that are going to be tangent to this boundary. Not tangent, but just touching it, right? And then another one would be, say, looks like over here, something like that. Okay, the kind of thing that's happening there. The lowest value of the function, as long as this function is like smooth and the boundary, we're looking at at smooth, at least smooth sections of the boundary, or the entire boundary is smooth, right? What's going to happen here? The function looks like this function. The highest value of the function in this red area is going to be happening right here. That's going to be the maximum. We're also going to have another maximum occurring, well, a local maximum at least happening over here, but then it starts, let's see, actually that looks like, yeah, that's actually a local minimum. This here is a valley, and then so that would be like a minimum, and then over here looks like we're going to have, let's see, the values are going down, down, down. Let's see, 4 is a high point, but then it goes down to 3 and what's that? It's going to be higher. Looks like over here is a high point. Actually, follow that curve. Follow it around. This looks like it's going to be. That's going to be another high point, right? That's going to be something like the 5.5, right? And over here we have the value. It's going to be like 2, 3-ish, something like that. Okay. So here's the thing that's happening in all of those cases. The level curve is tangent to the boundary curve. When they're tangent, the normal lines are going to be pointing in the same direction. So remember the gradient is pointing like this. The gradient is going up to the high, oops, I'm getting it backwards. The gradient is in that direction. The gradient is going like that. The gradient is looking like this. The gradient is going like this. In all of these cases, the normal line to the curve is parallel to the gradient vector, and that is the idea behind Lagrange multipliers. We want to find points on the boundary where the direction of the normal line is parallel to the gradient at that point. And so so now we're going to kind of set up the method. Okay, so the idea is if you have some function f of x, y, you want it to be maximized, in fact, or minimized, subject to some other constraint g of x, y equals k. So that's an equation, that would be a curve in x and y. So we're looking for some point x0, y0 where the gradients are parallel. And so they don't have to be equal to each other. So we put in this lambda parameter, which is like a scalar. So the gradient of f of x0, y0 equals lambda times the gradient of g of x0, y0. What this is going to give us is actually a handful of equations, and we have to solve. Here it is written a little bit more formally. Okay, so then this is what we do. This is the method of Lagrange multipliers for a function of 3 variables. For a function of 2 variables, it's the same thing except you just don't have a z. If you want to find the maximum or minimum values of f of x, y, z, subject to g of x, y, z equals k, as long as these exist and as long as the gradient of g isn't going to be the 0 vector everywhere. So we're going to first, solve the system delta f equals lambda times delta g, and also the g of x, y, z equals k. So this is going to be a system of equations. It would be, in this case, it would be four equations, 3 coming from the first, because you have a vector equal to a vector, so that's going to be 3 equations, and then you have a 4th equation. And then you test the values of f at the points. Right? You're going to have, you're going to ultimately find the value of the function is going to be maximized at some of the points and minimized at some of the point. You'll find the maximum and minimum values that way. So this is the idea, and let's just see. A point to be made is we don't really care about what lambda is. In the end, you will probably solve and get lambda sometimes. You'll find the value of lambda. But you don't need to find the value of lambda. You need to find the x and the y at the z, or just x and y if it's a function of 2 variables. So here's some examples. All right, the rectangular box with no lid is to be made from 12 meters squared of cardboard. Find the maximum volume that's possible. This might look familiar. We looked at this in the previous section, but now you'll see finding the answer using the method of Lagrange multipliers, I think, makes it a little bit easier and frankly a little bit more fun. So what we do is we find the restriction, and that the restriction is going to be, in our case, this function g of x, y equals k, which is the fact that the surface area total, which is going to be xy plus 2xz plus 2yz equals 12. This is our, sorry, it's a function of 3 variables, so let me clarify that. So, right, it's a function g of x, y, z equals k, that's this, and then we have our f, this is the function of x, y, z is just going to be x, y, z. It's the volume. That's what we're trying to maximize. So we're going to set up an equation that's the gradient of f equals lambda times the gradient of g. And what is the gradient? It's a vector, right? So we have, this actually gives us 3 equations. The gradient of f is the partial derivative with respect to x, with respect to y, and with respect to z. So the partial derivative with respect to x is yz equals lambda times the partial derivative of g with respect to x, which is going to be what? We'll have y plus 2z. Y plus 2z. Okay, and then going down the line, we're going to have the partial derivative of f with respect to y is going to give us xz, and that's equal to lambda times y times, let's see, lambda times x plus 2z, and then lastly we're going to have xy, what's the partial derivative of f with respect to z, and that's equal to lambda times the partial derivative of g with respect to z, which is going to give us 2x plus 2y. So with all of this, we then go ahead and try to solve the equation. So here's our first equation, right? And then we have these other 3 equations. Okay, what we can do is notice that these 3 equations here, we can make the left-hand side x, y, z by multiplying the appropriate thing on the right-hand side. So what I mean is, if we multiply by the first equation by an x, you get x, y, z equals lambda times xy plus 2xz. For the second equation, you get xyz equals lambda times xy plus 2x. Sorry, that's going to be 2yz multiplying through by a y, and then for the third one, you'll have xyz equals lambda times 2z plus 2xz plus 2yz. Yeah, so okay. So given all of this, we realize, of course, that we know that it's not possible for lambda to be equal to 0, right? Because if lambda was 0, then the volume of this box would be 0. Okay, so that's not the case. If lambda is not 0, then it must be the case that the only way these things are going to be, well, these would be equal as long as we need these factors to all be equal to each other. So if we write that out, we can see, let's take the second two, and these are going to give us xy plus 2yz equals 2xz plus 2yz, which you can cancel these terms, and what we get then is, and if you can divide by x, now we'll have y equals 2z. And so we can actually get a similar kind of fact from, if you can take the first and the third equations in your xy plus 2xz equals 2xz plus 2yz. And you realize, oh, I can cancel these 2xz's on both sides, and now I can divide both by y. What I'm going to get is x is going to be 2z also. So what I have, if I plug in all of these into this first equation, it's going to be 4 times z squared. This is to say I'm plugging it into this xy plus 2xz plus 2yz equals 12. I have 4z squared plus, let's see, 2xz, that's going to be, well, 4z squared plus another, 4z squared equals 12. So it turns out that z squared is equal to 3. Sorry. What I have there, z squared is going to be equal to 1, right? So z is going to be equal to 1. Then that means y has to be equal to 2 and x is going to be equal to 2. That's going to be the solution for this equation. That's going to maximize this box. So, wild, right? You can then, this is the only, you can see how like other values wouldn't, well, you can get these equations to be equal when x and y and z are zeros, but of course that's not going to make any sense for solving this thing. Okay, let's look at this little example. We're going to find the extreme values of this. Okay, so we're going to look for the extreme values of this other function, x squared plus 2y squared, on the curve x squared plus y squared equals 1. So to be clear, our gradient of f is the vector 2x comma 4y, right? And the gradient of g, now g of x, y is here, gradient of g is going to be 2x comma 2y. So when we set gradient f equal to lambda gradient g, this is just another way of saying 2x equals lambda times 2x, and then 4y equals lambda times 4y. And then, of course, the other equation is x squared plus y squared equals 1. Okay. Now, we notice right away that this first equation gives us either, so we can either lambda equals 1 or x equals 0. That's the only two ways that that first equation is going to be true. I think I made a little mistake on the second equation. I did. This should be lambda times 2y. Okay, so we look at cases. What if lambda equals 1, right? What does that mean? Well, if lambda equals 1, then that means if you plug that into the second equation, that means 4y equals 2y. That's only going to happen when y is equal to 0. And if y is equal to 0, then if you take that and plug it into the third equation, you have x squared equals 1. That means x is going to be plus or minus 1. On the other hand, if x does equal 0, you can, if x equals 0, then you know that, well, y has to be equal to, let's see, let's just be clear on that. If x is equal to 0, well, in the last equation, you just have y has to be plus or minus 1, right? Because that means y squared equals 1. So what we have then is 4 points. We have 1, 0, we have negative 1, 0, we have 0, 1, and we have 0, negative 1. Those are our 4 points x, y, and so we're going to evaluate f of x, y for all of those and see what we get. So you can see we're going to get 1 for the point 1, 0. Actually, for negative 1, 0, you're also getting a 1. And for 0, 1, we're going to get 2, and also for that. So you can see that these 2 points, those are the absolute max values, and then these two values are the absolute minimum values. Okay, so if we extend this a little bit and look at what about this function on the entire disk, x squared plus y squared less than or equal to 1, what we need to do now is consider where the, well, we already know what the gradient, right? The gradient of f was 2x plus 4y, sorry, comma 4y. And if we are looking for critical points of the function, the only critical point is the point 0, 0. And f of 0, 0 is 0, of course. So in fact, if we're looking on the entire disk, we know that the absolute min value is 0, and the absolute max value is 2 on that full closed disk, right? If we're considering the interior points of that circle. All right, so if you're trying to find the extreme values of some function on a region, we look for critical points within the region, and then we can use Lagrange multipliers to find the extreme values on the boundary of the region, and then we can just compare. All right, so let's say we have a sphere, and we want to find the points on the sphere that are closest or furthest away from some other point, 3, 1, negative 1. So the distance, I'll call it, so the distance between some point in space and a point on the, and this point here is going to be the square root of 3, let's say x minus 3 squared plus y minus 1 squared plus z plus 1 squared. The thing that you can use, though, a fact that actually we can look at f of x, y, z, just the square of this, x minus 3 squared plus y minus 1 squared plus z plus 1 squared. Because when the distance is maximized or minimized, the square of the distance is going to be maximized or minimized. So we can actually get rid of that square root, and we can still look for points that maximize or minimize this other function. It'll still will be the same points. It'll just be easier to take derivatives and such. So let's find the gradient of this other function I'm calling capital F. Okay, so it's going to be 2 times x minus 3, right? And then we'll have 2 times y minus 1. And then we'll have 2 times z plus 1. and the gradient of g, and this function here, this is g of x, y, z. The gradient of that is going to be 2x, 2y, 2z. Now, if we were to set these equations, if we set the gradient of f equal to lambda times the gradient of g, what we get are the equations 2x minus 6 equals 2x. We have, we have lambda times 2x. Sorry about that. We have 2y minus 1 equals lambda times 2y. Oh, no, it's not minus 1. It would be minus 2. And then we have 2z plus 2 equals lambda times 2z. And then finally, of course, we have this last equation, which is x squared plus y squared plus z squared equals 4. Now, we can actually go through and, okay. So for each of these, let's actually divide these by 2 each. So we have x minus 3 equals lambda x. We have y minus 1 equals lambda y. And we have z plus 1 equals lambda z. I'm going to solve each of these for x, y, and z respectively. And so what we're going to get for the first one is if you have x minus lambda x equals 3, this gives you x equals 3 over 1 minus lambda. Similarly, for the second one, we're going to get y is equal to 1 over 1 minus lambda, and z is equal to 1 over, it's going to be negative 1 over 1 minus lambda. So what I'm going to do is just, I'll say like, I'll just let delta equal 1 over 1 minus lambda for simplicity, and I'm going to, so this would be 3 delta, this is going to be delta, and this would be negative delta. And I'm going to plug those in for this equation. So we're going to have, let's see, this third equation, I'm going to plug in the deltas, okay? So we're going to have 9 delta squared plus delta squared plus delta squared equals 4. So that means 11, that means delta squared is equal to 4 over 11. Delta is going to be plus or minus 2 over square root 11. All right? Okay, so thus what we have, if we have the deltas, we can plug those in for and to get our values for x. So one point we're going to have is the point, let's see, plug it in for x, we're going to get 2, that's going to be 6 over root 11, comma, we have, plug it in for y is going to be 2 over root 11, and then z would be negative 2 over root 11. That's one point. And then the other point would be the negative. So it's going to be negative 6 over root 11, negative 2 over root 11, and then we'll have positive 2 over root 11. Those are the 2 points. And you can verify that this is the furthest point, and this is the closest point. And you can check that just by plugging them into f of x, y, z, and to see what the distance comes out to be. So wild, huh? I like these. Okay, so now we'll look and see what you would do if you have 2 constraints, and actually you can generalize this to more than 2 constraints. Okay, so if you're going to have to find the extreme values of f of x, y, z subject to 2 constraints, g of x, y, z equals k, and h of x, y, z equals c, some values, what you're going to do is for your first equation, you want to have the gradient of f is equal to lambda times gradient g plus mu times gradient of h. And then you add on the second, those other two equations, so that in total then you would have 5 equations you have to slog through. And again, you don't have to necessarily find the values of mu and lambda. We're just looking for values of x and y and z that are going to be solutions to this system. So let's take a look at an example. Okay, let's look for the extreme values, or the points where the extreme values take place of this function f of x, y, z, x plus 2y plus 3z. On the curve, that's the intersection of this plane and this cylinder. The plane x minus y plus z equals 1, and x squared plus y squared equals 1. So we're going to find the gradient of f first off, right? And that's going to be the gradient, the partial derivative with respect to x is 1, the partial derivative with respect to y is going to be 2, and the partial derivative with respect to z is 3. The gradient of g, right, that's this function here. This is our function g, and this, by the way, is h. The gradient of g is going to be 1, negative 1, 1, and the gradient of h is going to be 2x, 2y, and a 0. So the equation that we have would be, so when we say gradient f equals lambda times gradient g plus mu times gradient h, what this comes out to be is 1 equals, let's see, lambda times 1 plus mu times 2x. And then we have 2 equals negative lambda plus mu times 2y. And then the third equation gives us 3 equals just lambda. So that third equation actually, boom, you've got lambda, because it's lambda times 1 plus 0. So with that, we can plug that in for lambda in these two equations. We had 1 equals 3 plus mu times 2x, and that's going to be negative 2 equals mu times 2x, or well, we can have negative 1 equals mu x. Okay, then the second equation is going to give us 2 equals negative 3 plus mu times 2y, which is going to be, I had 5 to both sides, or sorry, I had 3 to both sides. You're going to have 5 equals mu times 2y. So we would say mu y is going to be 5 over 2. Okay, so with those, we should be able to, let's see what we can do. We can solve for y. Actually, we can take both of these actually, and we can write, say, x equals negative 1 over mu, and y is going to be 5 over 2 mu. And with those, we should be able to see if we can solve for mu, right? Well, you do that by plugging those into the function h. And so x squared plus y squared equals 1. If we have x squared plus y squared equals 1, that's going to be 1 over mu squared plus 25 over 4 mu squared equals 1. And we multiply this first fraction by 4 over 4. What we get is 29 over 4 mu squared equals 1. 29 over 4 equals mu squared. So mu is going to be plus or minus root 29 over 2. Well, with that, we have the ability to solve for all the values that we need, right? That means x is going to be the negative reciprocal of that. That's going to be negative 2 over root 29. Y is going to be, well, actually, I should say positive or negative, right? If x is negative, so this is going to be 2 possible values, I should say, or 2 over root 29. If you plug in positive root 29 over 2 into this, what we're going to get is, let's see, the 2 that's going to 5, we're going to have 5 over root 29 when you plug in when mu is equal to root 29 over 2, and then we're going to have negative 5 over root 29. And so lastly, to solve for z, you can just get z equals 1 minus x plus y, right? And so plus 7 over root 29, and we'd have 1 minus 7 over root 29. Yeah, that makes sense. So, okay, what we've got is we have 2 points. And now it's just a matter of plugging those in to the equation and seeing where we have maximums and where we have minimums. Okay, so let's just call the first one 0.1, the second one 0.2, and you can see that f of p1 is going to be, let's see, when you plug in that, what do we get? It's going to, well, at the end, 3 times z. If z is the biggest, it's going to be largest. I'm thinking, especially with y, yeah, this is going to be a maximum. This is going to be a maximum, and f of p2 is going to be a minimum. I'm judging that based on the fact that the only you want your z term. If your z term is the biggest, then you're going to probably get this largest, and when you have 3z, that'll make the biggest difference. But anyway, you can actually plug this into a calculator and evaluate it. That does it for Lagrange multipliers, but we have to get more practice doing this, so we'll do that together. All right, I will sign off from here. Bye.